Have you heard of this term anthropogenic? Despite its meaning, this term is very rarely used in a positive context. Anthropogenic means something that comes out of collective human activities. Often, pollution is something that is referred to as anthropogenic in nature. But when you consider even pollution, the anthropogenic activity was not to cause pollution. The intent behind the collective human effort was not to cause pollution. The mind that gave us this anthropogenic activity did not give us to cause pollution. The collective human mind that unfortunately led to this pollution gave us an efficient and a safe mode of transportation. So the transportation and the different modes of transportation we see is also anthropogenic in nature. And this mind that gave us an efficient, safer and at times luxurious mode of transportation, if directed properly, if motivated properly, can also come up with ways to manage the ill effect of the positive thing that was generated through this anthropogenic activity, this collective human effort. So, to put it simply, the mind that gave us the anthropogenic the effort that gave us good modes of transportation, the same anthropogenic effort can be managed or directed towards managing the ill effect of the transportation. Now, what we are going to see is the pinnacle of such collective effort, such anthropogenic effort, wherein we are not going to bring in anything external, anything profitable into play. We are going to allow waste, two forms of wastes, to battle out with each other and ultimately annihilating each other. So that is what we will be considering in this session. So the mind that gave us something profitable, when directed to managing the ill effect of this profitable thing, has come up with an approach collectively wherein the waste cancel out each other, ultimately neutralizing the ill effect. So in this session of metallurgical waste management, what we have been considering is the ways to manage blast furnace slag. Now in this session, we will be considering how blast furnace slag can be employed to neutralize other forms of waste. Now this session is going to be something similar to that of a survey-like session, wherein we will not get into the specifics, the nitty-gritty aspects of the different ways we can use blast furnace slag to manage other forms of waste. We will not be getting into the specifics of it. We will be surveying it. Now, when we consider how blast furnace slag can be deployed to manage, to annihilate the other forms of waste, there are three different approaches we could adopt. One is blast furnace slag without any alteration to its chemical or physical or mechanical properties or features. We can directly deploy them, and by their inherent features, they will be able to manage certain forms of waste. So that is what we will be considering as in the first session. So we are taking our blast furnace slag without altering any of its chemical composition or its physical features. We are going to deploy it, and because of its inherent properties alone, it is going to manage certain forms of waste. That is something we will be considering. And secondly, we are going to modify some features of this blast furnace slag, and this modification is going to allow us to tackle even broader spectrum of wastes. So that is something we will consider secondly. And finally, we will be treating the blast furnace slag, the waste that comes out of iron making, as a raw material, and from that we are going to extract or generate different forms of components, and which are going to ultimately tackle the wastes. So we are going to use blast furnace slag as it is, as without any modification, without any alteration. That is one way of managing the blast furnace slag, and this slag in all these three cases, without any modification, with some modification, and using it as raw material, completely derived form. In all this, we are going to use to manage different forms of waste. So one way is without disturbing the blast furnace slag. The other way is with slight modification, and third way is treating the blast furnace slag as a raw material, extracting, bringing out something out of it, and finally using that to manage different forms of wastes. as a raw material, or rather in its innate form without any modification, the blast furnace slag can be used to extract, to trap heavy metal ions, particularly the heavy metal ions like lead and cobalt. Now, if you consider the ill effect of lead, the lead some of you might be already aware of is an hazardous substance. It is not only hazardous to us, which we often treat as primary, it is not only hazardous to us, but it is also hazardous to the environment. The lead essentially affects our central nervous system, and it also affects our lungs. On the other hand, cobalt, it causes asthma. When exposed to a level that is greater than permissible, it causes asthma, and it also affects our liver. So these two have a direct effect. These heavy metal ions, particularly lead and cobalt, have a direct ill effect on our system, and also they affect our environment. So in order to reduce the amount of lead and cobalt in water, blast furnace slag has been used. So there is not much preparation involved in deploying blast furnace slag to treat water that is contaminated with lead and cobalt. All that you have to do is, all that has been done in this study is, the blast furnace slag is broken down into pieces, it is washed, and it is dried. So the reason it is broken down into pieces is not in the specific order, but the reason it is broken down into pieces is because the surface area that is exposed to water needs to get increased. So essentially it is broken down into smaller pieces. So you take your blast furnace slag, you wash the surface impurities, you dry it out, and you break it down into pieces. So that is essentially what is done as the preparation goes, and then it is mixed with water that is rich in, or that is contaminated with, lead and cobalt. And what essentially happens is, there is something called as an ion exchange that happens that allows the trapping of the heavy metal ions. So what happens is, this blast furnace slag loses his H plus ions. Its H plus ions it loses, ultimately gaining a surface negative charge. And at the same time, the lead and the cobalt are in a form with an hydroxide ion present in it. So you have a form of lead and cobalt with a partially positive charge to it, and after losing H plus ion, you have these blast furnace slag particles with a partial negative charge on it. So because of these difference in charges, you have an electrostatic attraction, ultimately leading to a formation of metal silicon complex. So it is the form of silica that is responsible for the attraction or the formation of the metal complex. So the ion exchange happens wherein the blast furnace slag particles loses H plus ions, and in the place of H plus ions they gain PbOH plus. And this is possible because of the structure of the silica that is the primary component of our blast furnace slag. So just by dissolving particles of blast furnace slag in water contaminated with lead and cobalt, we are able to reduce the amount of lead and cobalt present in the water. So essentially we are doing water treatment, wastewater treatment, using our blast furnace slag, which in itself is a waste. Now here you can see how the absorption happens when we have different amount of blast furnace slag present in the system. And of course, at certain concentration of the blast furnace slag, we have an efficient adsorption. So this adsorption is essentially the formation of metal silica complex on the surface of the blast furnace slag, thereby trapping both lead and cobalt. Now this trapping behavior, like I said, is primarily based on because of the structure of silica. And because the structure of silica is common across all forms of blast furnace slag, this behavior can be used to also trap other metal ions like copper, zinc and cadmium. Now, of course, copper zinc is something that is nutritional in nature. Some amount of copper and zinc is good for our body as well, and it's good for plant as well. But beyond a certain limit, it becomes hazardous. Cadmium, even in trace elements beyond the level of these traces, it's going to be hazardous. It's going to affect our central nervous system. So when you have a water that is contaminated by these elements beyond certain limit, then to treat those water sources, we can use our blast furnace slag. And the way the blast furnace slag operates is similar to how it operated in, or with rather, lead and cobalt. So essentially, even with copper, cadmium and zinc, the way these elements are removed from water is by forming a surface complex through ion exchange. The structure of the silica allows for such surface adsorption and formation of the complex, thereby reducing the availability of copper, cadmium, zinc, lead and cobalt for other purposes, meaning the bioaccessibility, the accessibility of these metal ions to the biological entities like us or animals or plants gets significantly reduced because they get trapped on the surface of our blast furnace slag. So you are tapping in the blast furnace slag, or the blast furnace slag is used to trap all these heavy metal ions. So in other areas, their concentration is going to get significantly reduced. So what it essentially means is the bioaccessibility, the accessibility to other biological entity is significantly reduced. Now, apart from these heavy metal ions, when we talk about the contamination of water, one other component that contaminates water is phosphate. Now, again, the contamination of water because of phosphate is an effect, is an anthropogenic effect, and the source of it, as mentioned here, can be mining, mineral processing, that is all the metallurgical aspect to it, and also something like fertilizer production. So what essentially phosphate does is, it does something called as eutrophication. Here it is unfortunately mentioned wrong, it's eutrophication, which means it takes away all the oxygen content in the water, thereby affecting both plants and fishes in the water body. It reduces the biodiversity in the water body. So we are talking of using blast furnace slag for water treatment. We have considered heavy metal ions. Now, one other critical component that affects the living biological entities in the water body is phosphate, and now we are going to deploy blast furnace slag to address this particular form of contamination, the phosphate contamination in water. The way the phosphate contamination in water is addressed by the blast furnace slag is, the form in which phosphate appears in water is in the hydrolyzed form. Now, in the hydrolyzed form, the phosphate forms salt with calcium and aluminium, which are again the components of blast furnace slag. So if you consider what constitutes a blast furnace slag, if you could recollect, it's comprised of, it is made purely or largely of silica, silicon dioxide, and we have calcium oxide and aluminum oxide. Now, calcium oxide and silica oxide, they form salts with the hydrolyzed phosphate that is present in water. The phosphate, the form of phosphate that presents in water, that contaminates water, is an hydrolyzed form of it. This hydrolyzed form ultimately reacts with calcium and aluminium oxides, ultimately giving us aluminium phosphate and calcium phosphate. So the form of phosphate that causes eutrophication, that removes oxygen from the water, is significantly reduced because these phosphates are now transformed into metal salts, primarily calcium metal salts and aluminium metal salts, thereby reducing again the bioaccessibility or the ill effect of phosphate. Now, these, whatever examples that we have seen so far, they have been fairly recent. So it's just within few years, these have been discovered, how blast furnace slag can be efficiently used to get rid of heavy metal ions. But if you consider this particular way of managing the blast furnace slag, how blast furnace slag can be deployed to control the amount of phosphate in water treatment, this has been around for a while. And for that reason, this particular approach has not only been considered or studied on a laboratory scale, but it has been also studied in a large scale. So people have built horizontal filters using blast furnace slags. So they have considered granulated blast furnace slag, and they have built horizontal filters. And they have used this horizontal filters to build or to treat water that ultimately gets into a pond. So we have a pond which is something that is made or built artificially in order to store water. So these are not like naturally occurring ponds. These ponds are artificially built to manage the waters, to allow or to stabilize some wastewaters. So our wastewater can comprise of several components, and some components can be stabilized if we allow the water to interact with sunlight, if we allow some components in the water to settle down. So when we consider wastewater, it is not always that the wastewater has some dissolved contaminants in it. It can have mud particles which are largely inert in nature, which when allowed to settle down will settle down. So in order to allow such contaminated water, such water with colloidal particles in it, inert colloidal particles in it, we artificially built some ponds. So these are referred to as waste stabilization ponds. However, if in these water, if phosphate is mixed, phosphate will not settle down on its own. So before using or before collecting this water into these ponds, this water with phosphate mixed in it needs to be treated. So what people have done is people have built such horizontal blast furnace filters. So you can allow the water to flow through this horizontal blast furnace filters, and as they flow through the blast furnace filters, the phosphate gets collected as metal salt, and the water with less amount of phosphate is ultimately gets collected into this pond here. Now this pond devoid of phosphate might have other inert colloidal particles, other inert met particles in them, which when stored as the pond like this get ultimately settled down. So this is one of the place where the blast furnace slag in the form of a filter is deployed as a water management or water treatment facility. So our understanding of how blast furnace slag can be used to manage the amount of phosphate content in water has now been deployed on a larger scale, particularly when waste stabilization ponds are used. So when you use blast furnace filter, you are essentially getting rid of the phosphate content, and all the rest are allowed to settle down in the pond. Apart from the water management activities that primarily involved heavy metal ions and that of phosphate, the blast furnace slag is also being used to address the waste content that are not so straightforward. Of course, when we talk about heavy metal ions and that of phosphate, they come as a byproduct of human activities. But there are pharmaceutical waste that essentially come out, or they are more complex in nature from a chemical perspective. When we talk about these pharmaceutical waste like carbamazepine, diclofenac and ibuprofen, so what these are not a straightforward chemical content like that of phosphate and that of heavy metal ion. Carbamazepine is essentially a drug that is given for a patient with mental instability. Diclofenac or diclofenac is rather a drug that is given to reduce pain. And of course, many of us know what ibuprofen is. So these are chemically complex in nature, and of course these are outcomes of anthropogenic efforts. And recent research has found that when we let out these chemically complex pharmaceutical substances, and if our water is contaminated by this excess of these chemically complex substances, chemically complex pharmaceutical compounds, our blast furnace slag is able to reduce its access. It's able to restrict these complex pharmaceutical compounds. So as you can see here, the removal behavior, the efficiency of our blast furnace slag when compared to other suitable removal agents is rather on par with the other agents. So we have other agents like, for instance, sand has been considered, but you can see the efficiency is significantly low. But when you compare the blast furnace slag with that of other specifically designed agents, it's more or less on par or relatively less, but to a manageable, to an appreciable degree, our blast furnace slag is able to remove such chemically complex pharmaceutical compounds. So blast furnace slag, which is nothing but a waste that gets primarily generated out of a metallurgical process, can be used to manage contaminated water, and this contaminated water is not rather primitive in nature. It just not only contains that of heavy metal ions and phosphate. Even if your water is contaminated with pharmaceutical compounds like these drugs here, which are chemically extremely complex, our blast furnace slag is able to trap even these complex compounds as well. And the primary reason is because of its structure. It is predominantly comprised of silica, and silica has this unique structure to trap these complex compounds, complex pharmaceutical compounds, and thereby reducing their availability to biological entity, which we refer to as the bioaccessibility. So these blast furnace slag, they trap both heavy metal ions, phosphate, and also complex pharmaceutical drug, which I'm really afraid to pronounce again. So these are ways the blast furnace slag, a waste itself, can be used to treat a wastewater or contaminated water with heavy metal ions and other forms of hazardous wastes. Now what we are going to see in the upcoming session is what happens if we modify this blast furnace slag. So far, the way we have deployed blast furnace slag in all these applications, either to remove heavy metal ions, or to remove phosphate, or to remove even these complex entities, the way we have deployed blast furnace slag is just by cleaning them, drying them up, and breaking them down into pieces. We have not done any modification to the features of the blast furnace slag, the chemical composition of the blast furnace slag. We have just deployed them as they are, except what we just broken them down into pieces just to increase the surface area. Now what we are going to do in the subsequent sessions, or what we are going to discuss, is how efficient this waste is going to become when we modify them slightly, and where and all it can be deployed. So that is exactly what we will be considering in the upcoming session. Goodbye, guys.